times the P inverse. Okay, and you have the vector x0. So this is how the solution looks like, where this exponential of this diagonal of this bj's are the block matrices of the Jordan form. Okay, so where bj are Jordan blocks. Okay, where bj's are the Jordan blocks corresponding to the eigenvalues lambda j. Where and P, the columns of P are generalized eigenvectors. Right, so this is how we wrote the solution. That means each of this entry of this phi, okay, so each component of this phi will have each component of phi, okay, has functions of the form so say t power alpha, or if you write what did I write, t naught. If I write t naught, then it is t naught, t minus t naught power alpha. Right, so t minus t naught power alpha into the exponential of a into t minus t naught, okay, times the cos b into t minus t naught, where this lambda is a plus I, okay, eigenvalues, or it can be of this type, or it can be of this type, power alpha times exponential of a into t minus t naught into sine b to t minus t naught. Sine b into t minus t naught. So these are the a plus ib is the eigen values, and alpha is something which is less than the order of the matrix. Okay, so only when the eigenvalues are repeated, you will have the alpha positive. Otherwise, alpha is going to be 0. So this is how the components of this phi looks like. This is what we have seen. So that means I can write the norm of this phi t. Norm of phi t is it's a vector, right? So phi is a vector. So the norm is either you can write norm or you can write mod, or you can write mod phi. Mod is in Rn. So that is going to be less than or equals to some constant times e power at, okay, e power at into some t power p. What is this a? A is the maximum of all these aj's, where aj is lambda j is aj plus I bj. That's how eigenvalues look like, and the maximum of real parts of this eigenvalues, and p is the maximum of the pj's. Where this is depends on where this alpha comes from. So I can say that pj is the multiplicity of lambda j. Okay, multiplicity of lambda j. Okay, so you have an estimate like this. It is always true. So because each component of this looks like this, sine and cos are always absolute values less than or equals to 1, and t minus t naught power alpha, it looks like t power p. So alpha, I said, it depends on the multiplicity of the eigenvalue lambda. Okay, exponential of a is there, so that is exponential of at will be there. So it depends on whatever is the maximum value of a, that you take that. So that is going to dominate all these components. So the asymptotic behavior, so the easy consequence of this thing, either you can write as a remark or theorem, first theorem, basically says that the every solution xt goes to 0 as t tends to infinity if all eigenvalues okay, has negative real parts. So what happens if all eigenvalues have negative real parts? The maximum also is going to be negative. Okay. So the maximum also is going to be negative. Therefore, the solution here mod xt is going to be e power minus t times some constant times t power p, which goes to 0 as t tends to infinity. Okay, goes to 0 as t tends to infinity. So this is one. And the second one is every solution xt is bounded. Okay, bounded. If all eigenvalues, okay, so there are two types of eigenvalues here. One is that eigenvalues that are simple. Simple means they are not repeated. Okay, eigenvalues that are repeated. Okay, all eigenvalues that are repeated. Okay, because if eigenvalue is repeated and the geometric multiplicity is less, then there is a possibility of then you have the t power p. Okay, is coming as a coefficient for this, right? So p has negative real parts. And the simple eigenvalues means that which are not repeated. Simple eigenvalues have non-positive real parts. That means that they can have a 0 as a real part. The real part can be 0 for them. Once if it is 0, real part is 0, then it will have sine t and cos t as this thing, and they are bounded, but they don't go to 0, right? So you can allow the eigenvalues, the sum of the eigenvalues, the simple eigenvalues, to have 0 real parts if you are looking only for the boundedness of the solution. Okay. So this this is the asymptotic behavior. Basically, this is the kind of asymptotic behavior that we are going to see when we study the stability of the solutions, or we are going to call it as the phase plane analysis. I will tell you after this, maybe tomorrow's lecture. So I'm introducing the what is called what is the terminology and how to look at the asymptotic behavior of the solutions for the linear systems. Okay, so this is the observation which is coming from just this fact that phi t is going to be less than or equals to c into e power at to t power. Okay, so once we have this homogeneous system, now we can even take the, as somebody was asking, a system with variable coefficients. Okay, so this is normally, this is very important in the sense that these are called asymptotic systems. Okay, so that is, you are going to, I'll tell you what is the importance of the system. The importance of the system is that you are able to write the non-homogeneous, system with variable coefficients in this form. Okay. Say as a t tends to infinity for large t. Okay, so that is here A is a constant matrix. A is constant matrix, and B is variable. So this comes in the is a matrix, generally a matrix with constant matrix with continuous coefficients, entries, elements. So this comes in the place where we talk about asymptotic stability. Okay, so asymptotic stability. So I'll introduce these things very formally, the formal definitions later. So in this case, what happens if A is a constant matrix and B is a matrix with continuous elements? Okay. So in this case, what we see is that you can write the solution. Okay. You can write the solution. How do we write the solution for this? So you take the x bar on the left hand side, ax on the left hand side, okay, minus ax, which is equals to b into x, okay, and you multiply this by e power minus a to t, because you know what is right. So this is what we had the formula of variation of parameters formula, right? So I need not to repeat these things again. So by variation of parameters formula. So by variation of parameters formula, basically the idea is you can write the formulas, okay, like in the scalar case. Okay, so multiply by e power 80 and so on. So how the solution looks like? The solution looks like we have seen earlier. The xt, okay, is going to be the e power 80 into x naught. So we call this as x at 0 is x naught. That is the initial condition, plus 0 to t. This is the non-homogeneous term. Just think that this is a f. Just think that this is your f. Okay. So you can write here the e power a into t minus s into bs into xs ts. So this is my f. This is my f. So this is how the solution, you can write the variation of parameters formula. Okay. So from here, we want to basically talk about what is the growth of this as t tends to, where does it goes to as t tends to infinity. Okay. And also we want to talk about whether this is bounded. Okay. So under what conditions this is going to be bounded. Okay. So if I write this norm, right? So if I write the norm here, so we have the xt. Each vector looks like the vector, each element we can write like a vector here. E power 80, which is a matrix, times x naught plus t naught to t e power t minus s, okay, bs into ts. So when I take the norm of this, means that each vector you have mod x1 t square plus mod x2 t square, like that to the whole square root. Okay. So this is also now a matrix multiplied by this thing is going to be another vector. So we can write that this thing as the norm of the matrix, okay, times the this one. So these are some of the simple things you can verify. That is, if you have any matrix, okay, and a vector, say if I take this, and then write the norm of this. Norm of this means that treat this, this is a vector now, right? So this is a vector. So if I write the norm of this, okay, so you can write this to be less than or equals to the norm of this b times norm of this b, small b. So these are not difficult things. You can check this. Okay, so this is a matrix. This norm b is nothing but just treating the b as a vector. Okay, put all the elements as all the elements of the matrix as a n square vector. Okay, and then write the norm of that. And this is also you have you can write the norm on the outside, and right. So you can write this as plus t naught to t, as this is simply a matrix e power a into t minus s. Okay, and this is again norm bs into norm xs. So in this estimates, we suppose if this is this is the first theorem, we will call it as if e power at, the fundamental matrix, okay, if this is bounded and the integral 0 to infinity ps ts is finite, okay, then any solution is going to be bounded. Okay, so if this is e power at is bounded, we can say that this is less than or equals to a constant c, and this is also less than or equals to c. This is less than or equals to constant c, and you have the norm bs. If this is bounded, then you say that the solution is going to be bounded. So let me write one more step here. So what we get as a proof. So the first step is going to be norm xt. Okay, so this is less than or equals to c times norm x naught plus c into 0 to t of norm ps into norm xt. Okay, so from this we apply the following Grunwald's inequality. Grunwald's inequality. I already did this earlier. Ut less than or equals to pt, suppose, plus the integral 0 to t into q into u ts, if this is true. Okay, if this holds, then u is going to be less than or equals to p into t plus t naught p into q to e power tau to t to q, okay, to dt. So this is and moreover, if p is a non-decreasing, okay, p is a non-decreasing function. If p is non-decreasing, then you will have ut less than or equals to pt. This becomes multiplication, exponential of 0 to t into q. Okay, so we will apply this inequality. Okay, so with u equals to this as u, okay, and this as p, and this is q. Okay, and then you have ut less than or equals to pt plus some constant c times q into the u itself. Okay, so when we apply this inequality, we get because now p is simply a constant. Okay, so it satisfies this. Therefore, you get this ut less than or equals to pt into this. Therefore, applying this, we get norm x bar t less than or equals to c into norm x naught into exponential of 0 to t. And we know that this is given to be bounded. Therefore, this is bounded. So this is going to be less than or equals to some, okay, times this bound as t tends to, for all t, right? Because it is given that 0 to infinity of b is bounded. Okay, so this shows that xt is going to be bounded. So similarly, one can also show basically using that integral and the Grunwald's inequality. Okay, suppose that real parts of eigenvalues are negative. That means basically the e power at, norm e power at goes to 0. Okay, so you can write the real parts are negative or norm e power at goes to 0, and also the norm bt goes to 0. Okay, as t tends to infinity. then all solutions x t goes to 0 as t tends to infinity. So let me write the proof one by one. So norm at goes to 0, norm exponential of at goes to 0. So this implies that there exists a delta greater than 0 and such that, and so this since this goes to 0, you have the not this goes to 0, I need the eigen, anyway this will have the eigenvalues, right? Exponential of eigenvalues. So this goes to 0 means that the eigenvalues are going to be negative. So in that case, what we will have is that norm e power at, okay, so less than or equals to e power minus delta t, okay, for all t greater than or equals to 0. Because I am anyway taking A to be a scalar matrix. Okay, so this is true. This is what I also said earlier. So all the eigenvalues are going to be negative. Therefore, real parts of eigenvalues are going to be negative. Therefore, we will have this. Then also norm bt goes to 0. So this implies that for any epsilon greater than 0, you have one t1 greater than 0 such that the norm bt is less than epsilon for all t greater than or equals to t1. And now go to that integral, the equation, and then that estimate. Okay, we had the estimate like this, which is less okay, integral into norm bs to x. So you apply the estimates in this, then we get c into norm x naught, okay, plus the so c norm x naught into e power minus delta t plus again c into 0 to t e power minus delta into t minus s to norm bs into norm xs. Therefore, so this implies e power delta t into xt. Multiply on both sides. So see, you get c into norm x naught plus c 0 to t e power delta s into norm bs into norm xs. Okay, so but we have the norm bt is going to be less than epsilon only for t greater than or equals to t naught. Therefore, we can write the second integral into two parts. C into, say, the 0 to t1 plus t1 to t. Okay, so this whole thing is now going to be a constant. So you can take this to be your pt in the Grunwald's inequality, and this is your u, and b is your q. Okay, and apply the Grunwald's inequality. When we apply the Grunwald's inequality, so implies that we will get ut less than or equals to c times rp, that is okay, so c or p, I call this as, this is your c or p, the Grunwald's inequality, c times exponential of t1 to t into c epsilon ts. So which is going to be, which is like c into e power c epsilon into t minus t1, which actually is small as epsilon right? So that's how you have the u is less than or equals to t like this, but u is what I said, u is e power minus delta t into xt, right? So that is e power delta t into xt. C epsilon into, right? So when we take now norm xt, so this is going to be c into exponential of epsilon c into t minus t1 into e power delta t minus delta t, right? So when it goes to the other side, right? So we can now, epsilon is in our hand, so you can choose epsilon so that this whole thing actually is going to, this term is going to dominate, and therefore you get this goes to 0. Okay, so this goes to 0. So this is how this asymptotic behavior of this linear system of equations are one can do. Also, you can have, we need not have the Grunwald's inequality can also be applied in case of non-homogeneous systems where you don't have this, you don't have b into x, but simply f. Okay, so that you can take it as an exercise and do, where you have in place of this you have f. So look at the try to look at the conditions on this f, so that have the asymptotic behavior of the solutions. Okay, do you have any questions? Is anyone online or just logged
Yes,
in?
sir. Yes, sir.
No, sir.
Previous class में है.
Some of you are available.
We are online, sir.
Okay.
Yes, sir. We are online.
Yeah. So I already shared the notes with you, and there are some small spelling mistakes and things like that. So after correcting that, I will send you the notes once again.
Sir, I have a doubt in last class.
That's what I asked you in the beginning. If you have any questions in the previous class, tell me.
Now, sir.
Yeah.
अभी पूछ ले, क्लास के लास्ट में पूछेंगे.
हाँ, पूछ लो.
ओके सर. सर जो रिमार्क, सॉरी, थ्योरम 1.1 है ना, नोट्स के अंदर पेज नंबर 16, वो है P, let P be the matrix generalized eigenvector of A as a column, then P equals to Pj P inverse, and e to the power at equals to P e to the power jt P inverse. And आपने जो क्लास में करवाया था उसमें ऐसा कहा था कि जो मैट्रिक्स है, मतलब जो e to the power at हम लिखेंगे उसको, तो वो फाइनाइट होगा.
फाइनाइट होगा
मतलब वो सीरीज फाइनाइट होगी.
Right. Then only it becomes a matrix, right? Otherwise the entries will have otherwise the entries will, I mean, it will keep on going as a series, right?
Yes, sir.
Basically the entries of this each entry will have a series, no? That series converges. That's what we call it as e power jt, right? If j is a Jacobian form, we said that what is e power jt in the previous theorem. We said, right, e power jt is nothing but e power lambda t into 1t t square by factorial to e power k minus 1. That's what I mean to say, that it converges to a matrix where each entry is going to have a series, and that series is going to converge. There are only finitely many kind of thing. It's not an infinite series. You can write that, no? So you see there are two ways to write this. A is you have A equals to Pj P inverse. Okay, so from this you write e power A into t. So if you assume that this is of this type, a square by factorial 2 into t square and so on. Substitute this a equals to this in this. So if you substitute this a in this, right, so you get p into j into p inverse, right? So you get I plus a is p j p inverse into t like this, no?
Yes, sir.
Yeah, so A square is going to be again P J square into P inverse, no? So on and so on. So this is what? You can write this as yeah, P inverse P into e power j into t into P inverse, right? Just as a series, no? And also we see that e power jt into P inverse is a solution. Therefore, and the system has a unique solution, therefore it has to be of this type. As a series it becomes like this. E power jt is e power at equals to P into e power jt into P inverse.
Yes, sir. That means we common P first, then P inverse or e to the power j t is thing. Then after this becomes.
Yeah. This is what we earlier also we had, right? So once if we have this is what happens in case of diagonal matrix also, and that's what we are seeing here also as a for the Jacobian matrix. So if you have the not Jacobian Jordan form, right? If you have a Jordan form, then you know what is this. So you write e power j and then take the P and P inverse. Therefore you get e power 8. And for a solution you have e power 80 into the vector x naught. So that is going to be P into jt P inverse into x naught. So you have the solution, which is maybe you call this as xt, which looks like this. Okay, the solution is exactly this.
Yes.
And for this to know, you need to know only the exponential. I mean, why this form is so important is that if you want to look at the asymptotic behaviors of xt, okay, so the asymptotic behavior of xt, how it looks like the bounds. Then I have this matrix times now x naught. And this matrix has this one e power jt. E power jt will have, again I said, exponential of at into sine and cos, or multiplied by t power t. Yeah.
Yes, sir.
Any other
So
questions?
one more thing. Sir, at the page of uh, 8 पेज नंबर कुछ जो आपका एग्जांपल है 1.3, ओके, सो वहाँ पे 3 आइगन वैल्यू है और 2 आइगन वेक्टर्स है, ओके। सो जो थर्ड आइगन वेक्टर हम जनरलाइज थर्ड आइगन वेक्टर निकाल रहे हैं, तो वहाँ पे जो हमने क्वेश्चन मतलब जो लिया है एक वेक्टर लिया है अल्फा टी प्लस बीटा e to the power 2t,
Right.
सो इसको इस तरह से क्यों लिया ये पूछना चाहते हैं।
Because you have to take the vector which is in the span of these things, right? For writing a generalized random vector, you take any vector in that, then you can find the one vector you have to take. So you take the vector in the span, how the vector in the span looks like, right? In the span of those two-dimensional, if you see the proof of this Jacobian, the Jordan, the proof of the existence of generalized eigenvector, no? It says basically there is a null space, there is a dimension, one dimension between the null space of eigenvectors and generalized eigenvector. So you have to take the vector. If you take a vector in the eigenspace, right, then you can find the a minus lambda I into v equals to u. So you have to take in the eigenspace. So in the eigenspace, how it looks like? It looks like alpha into e1 plus alpha beta into e2, or k1 e1 plus k2 e2. So you take that form, and then because it's an eigenspace, so k1 k2, and you write the system, it may have some conditions. So it basically says that you have to take those conditions into consideration, or you have to write exactly how the span of these two vectors look like. Then only we'll be able to find
Yes.
solution. Yeah, not
Yes.
for any vector.
So one more thing last,
Yeah,
जो
you may not be
आपने
able to
करवाया,
find. See, you may not be able to find the solution by taking one eigenvector from coming from the eigenspan of one eigenspan of one eigenvector. Okay, generalized eigenvector means that you have to take an intersection of both of them. That's what it means. That's why you are writing the
Yes.
k1 e1 plus k2 e2, and
Yes,
then
sir.
look the conditions for k1. Yeah.
सर वन मोर थिंग लास्ट जो आज आपने करवाया बी का नॉर्म कैसे लें, मतलब किसी मैट्रिक्स का नॉर्म कैसे लेंगे, वो एग्जांपल लेके
So
बताइए.
the norm, see the matrix, suppose if I, what is the meaning of a matrix norm? So if you have a matrix A, okay, so you write this as Aij, right? The entries. Huh? So what is the norm of A?
Yes,
Just
sir.
treat this as, treat these things as simply the vector. So write this as sum of mod Aij, okay, square and power half. This is what we do when it is a vector, no?
Yes, sir.
Yeah, so if it is a vector, this is what we write. So in the matrix, you treat that as a vector. Okay, so sum over ij equals to 1. This is a finite sum, I equals to 1 to n and j equals to 1 to n.
Yes, sir. Yes, sir.
Yeah, there are many ways to write the norms, though you can write the maximum and maximum of mod aij. But all these norms are, you will see that these metrics are going to be, all these things are going to be equivalent in a finite dimensional space. But I mean, that goes into a little bit of function analysis. I don't want to go. So you can just take this as a thing. Okay, so you can write any matrix A into, say, a vector x. Okay, and then you write, you multiply these two things and then write this kind of a thing, and you can use this Cauchy-Schwarz inequality to show that this is less than or equals to this into this. Okay, so you know the Cauchy-Schwarz inequality, right?
Yes, sir, we know.
So you can apply those things to show this kind of things.
Yes.
So in the next class, I will introduce what is called the stability, asymptotic stability and linear stability and all those things, and then I will use the things, what I spoke today about the asymptotic behavior of the solutions. Okay, so if you have no questions, let us take a break for today.
Thank you, sir.